Cameras. They come in many shapes, from really old analog cameras, system mirrorless cameras, video cameras. These all work really great when you use them for their intended purpose. Except this one, because it's broken. But I always wondered, how hard would it be to make my own camera? There are many approaches for this, and the one I picked is basing it off the Raspberry Pi, because it can be combined with a Raspberry Pi camera. And with this combination, I'm almost done already. Now this is a first generation Raspberry Pi, and I need a slightly faster one. And this is a first generation camera. This is actually a knockoff of a first generation camera. So the image quality is quite horrendous because this is a tiny sensor. So we decided to upgrade to the Raspberry Pi 4 and the HQ camera, because the HQ camera is the largest sensor that Raspberry Pi has available at the moment. So I made this prototype, and it looks like this. This is just a few pieces of wood to keep everything together. But this is the Raspberry Pi HQ camera with a CS mount security camera lens, the Raspberry Pi 4, and the 5-inch Raspberry Pi touchscreen. I've been working on and off on this project for about a week now to make it somewhat presentable. And the software is pretty nice. The case isn't, but it works for now. This really needs some cool designed enclosure for it. But to have a closer look at this, let's see. Yes. This is the front. This is a €50 security camera lens I found on eBay. This is the HQ sensor that I just screwed down on a piece of wood, and I made a slot here to fit the cable through. Then inside here, the flexes connect to the Raspberry Pi with, well, it's all connected the right way. And I have networking hooked up here, so I can SSH in and actually start the camera, because it's not a finished project. It works like this. Let's see if I can. I have a bit of an issue with the wiring here. I need something to put it on. Yes, this works. So now I will need to start the camera software with SSH. Alright, this is the camera software started. And you'll see there's a bit of latency, but for live production use. So you're now zoomed into the display of the Raspberry Pi. And this highlights the first roadblock I have with this software. This panel is a portrait native orientation. And the Raspberry Pi 4 does not have any hardware capabilities for rotating the output. And of course you can rotate your desktop environment if you're using that on this display, because those are generally OpenGL composited and they can just be rotated in the GPU. But for this UI, I'm bypassing the GPU basically. This is currently taking the stream from the camera module, and the kernel is forwarding the frames from the camera directly to DRM/KMS, and it will display that in a plane overlay. So actually still looking at the TTY here, but on top of the TTY is drawing the camera, and on top of the camera is drawing a frame buffer with this UI. And all the DRM planes cannot be rotated on the Raspberry Pi. On the Raspberry Pi 4 at least. They have a rotation property, but it only allows rotating by 180 degrees and not the 90 degrees I need. So you're actually looking at a part of the camera view here only. And if I focus the camera a bit, you can see it's actually working quite well, but due to lack of light, it's a bit noisy. So to have an actual demo of the UI, currently at the top it's showing the frame rate, the shutter, and the analog gain of the sensor. And with the show shutter speed and the max gain of the analog, it looks like this. And that's mainly due to light limitations. If I can probably light this up, make it drop the gain, or not, make it look into the light. Yes, you see the gain dropping now, and you cannot really see the noise reducing, but it does work. So on what will be the bottom of the screen, there's a few buttons. The currently only one enabled is thirds. That's giving the guides for the rule of thirds, and just tapping the buttons enables and disables this. This is the exposure overlay, and it should highlight all the pixels that are in the region of 50% gray as green. And zebra is for showing overexposed pixels. Let me grab the camera again. If I now overexpose it, the bars you see here are the zebras to tell you that it's clipping the sensor. And lastly, the focus, that is highlighting the edges in the image with red pixels. So you can see if you're in focus or not without actually zooming in to see how in focus you are. If I mess with it, you can see that it is showing which pixels are in focus and which are not. And you can of course enable multiple of these, but you will see the frame rate will drop because they are updated in sequence. And the focus assist is updated once every 2 frames. So the full update cycle with all 3 enabled is that once in every 4 frames all the layers are updated. But the camera view behind it is still running at a full rate. And that's due to the magic of KMS overlays, because it is rendering the camera feeds independently of the UI feeds here. So let's switch back to the not zoomed in lens. But the purpose of this camera is not showing a fancy UI, it is to actually output HDMI to a production switcher like this. So let's hook that up. I have one of the HDMI cables ready here. Unfortunately, the Raspberry Pi 4 has micro HDMI, which is not an ideal connector. So. And now if I switch the feed, actually, while that's going, I can probably hook up the second HDMI output. Unfortunately, that one has a really short cable. Alright, so now in this view, this is HDMI output 1 on the Raspberry Pi, and it should show the camera feed itself. And this is HDMI output 2, and that should do nothing because I'm using the internal monitor. Now let's start the software. And there we go. Now I have the camera feed here. Can I aim this slightly more interesting? All right, camera feed. So this is the intended use of the camera. Have it hooked up with HDMI to a switcher, pointed at something, and you have a camera that is not terribly great quality, but a lot cheaper than the professional ones. But since you can now not see this display, I can switch over the software to render the UI on HDMI 2 instead, so that will also be visible. So, restarting the camera now. And now I have nothing, you cannot see it, but I have nothing anymore on the display here. And now you're seeing here the HDMI output feed for the normal output, and here is the HDMI feed for the display. And this is outputting 1080p, but I'm rendering the UI, at 1280 by 720, because that's the resolution of the internal display. And hopefully you can also see slightly clearer how the UI works like this, instead of capturing a screen with a camera. And probably if I tap the right spots on the touchscreen, I should still be able to control the UI. Yes, there we go. So now you can see the output and the signal being in sync. This is currently all implemented in Python, and it needs a few more additional things to be implemented. Like at the moment it's not possible to tap one of the controls at the top row, like the shutter speed, to actually change it. It's only visible here. I do implement the HTTP API here for Blackmagic cameras. So it's possible to use any app that uses that API to change these settings. And through that it is possible to set a fixed exposure, lock the white balance, and change the gain. So I'm planning to work a bit more on this software, get all the extra UI bits implemented, and figure out how to generate Raspberry Pi images that have all of this pre-installed, so it's easy to deploy on your own Raspberry Pi if you have the Pi 4 and any camera, because this is not hard-coded to this specific camera, it's just the one I am currently using. Also, something that needs to be figured out is the optics, because this lens works, but it's not an ideal lens. It is, but what's written on here, it's a 5 megapixel lens quality, without any brand, of course. And even if the focus is perfect, this lens is just not terribly sharp. And the limitation here is the CS mount, which limits you to security camera lenses basically, and they are all not optimized for great picture quality. So the solution here is to either switch out the camera module to one with a bigger sensor and with an accompanying bigger mount, or find a way to source better optics for this setup. One of the solutions I found here for is the 1-inch eye, which is a very great project for connecting larger sensors to the Raspberry Pi. And one of those sensors is the 1-inch sensor, which is significantly better than what I'm using here, but still uses the CS mount. But that is a bit hard to source. And the ideal sensor for this is the Micro Four Thirds one that's made, that allows me to just use my regular MFT optics on this camera. But yeah, that adds a lot cost to this project, and also it is very hard to source. But it should work out of the box on this setup. Okay, so this is now recorded on the Raspberry Pi camera. I really need to come up with a better name for this thing. And hopefully this is working fine, because I no longer have audio monitoring this way. And I can see the monitor, but it looks really awkward if I look to it. So yeah, if you want to help develop this, it's pretty easy to get started, because it's just an off-the-shelf Raspberry Pi 4 and the camera module. And the display even is optional if you just use 2 HDMI outputs. And I currently have the code for this on GitHub. I will paste links in the video description. and also some of the links to the related projects. Ideally, I would have a bit better lighting setup to demo this, but I'm losing daylight. It's getting pretty dark outside now, and I'm using the horrible lighting in this room. So this is a bit more of a stress test for using this in bad scenarios, which is most likely most scenarios this will be used in. And yeah, if you try to help develop this, the code is pretty easy to read so far. It is on Git. Thanks for watching this video.